Welcome to DevOps Corner. You ever find yourself staring at your terminal, you type Docker build, hit enter, and just wonder, what is actually happening under the hood? Well, today we are going to peel back the layers, literally, and build a really solid mental model of the architecture that makes Docker images so incredibly efficient and powerful. Let's get right into it. So let's start with this common misconception. Is a Docker image basically just your app all bundled up in a fancy zip file? I mean, it's a simple way to think about it, and it kind of makes sense on the surface. But the reality is so much more elegant, and understanding that elegance is what really unlocks what makes containers a total game changer for developers and DevOps engineers. So here's the first big mindset shift you have to make. An image is not a single file. Think of it more like a complete, self-contained blueprint. It defines the entire file system and environment that a container is going to run in. This right here, this is the magic that finally solves that classic, super frustrating, well, it works on my machine problem for good. To put it a bit more formally, a Docker image is a static, read-only template. You can think of it like the perfect, unchanging recipe for your application. And from this one single blueprint, we can then stamp out dozens or even hundreds of identical, live, running instances that we all know as containers. Now, what's really fascinating is how this blueprint is actually put together. It's not just one giant monolithic block. Instead, I want you to picture a stack of transparent sheets, like the kind you'd use on an old overhead projector. Every single instruction in your Dockerfile adds a brand new sheet, a totally new layer to that stack. This idea of layers is the absolute core concept. All right, let's make this real. Every image has to start from somewhere, right? So this very first line from Ubuntu.20.04, it lays down the first and most fundamental sheet in our stack, the base operating system layer. Everything, and I mean everything, else is going to be built right on top of this foundation. Okay, next step. Our app needs some dependencies. So this run command here, it installs Python. What Docker does is it executes this command, it figures out exactly what files changed on the file system, and it captures all of those changes in a new layer, which it then places right on top of our Ubuntu base. The key here is we're not modifying the base layer, we're just adding a new one. And finally, the last piece of the puzzle, our own application code. The copy instruction creates the final layer in our stack, and this layer contains only our source files. And just like that, we have a complete blueprint. The base OS, all our dependencies, and our application code, all stacked neatly together into one single cohesive image. Now, here is maybe the most critical design choice in this entire system. These layers are immutable. Once a layer is created, it can never be changed. And that might sound like a limitation, but it's not. It is the secret sauce behind Docker's incredible efficiency and consistency. And this is a brilliant illustration of why that immutability is so powerful. Because that Ubuntu base layer is locked in and can't be changed. Totally different images, say a Python app and a Node.js app, can share the exact same base layer on disk. You don't store two copies of Ubuntu, you just store one. And Docker intelligently reuses it for both, saving a massive amount of storage space. Okay, so this should immediately bring up a huge question in your mind. If every single layer in the image is read-only and completely locked down, how on earth can a running container write log files, or create temp files, or modify configuration? How does anything dynamic actually happen? And the answer is just so simple and brilliant. When you tell Docker to run a container, it takes all those read-only image layers and it just adds one more thing to the top of the stack, a thin, empty, and most importantly, writable layer. This is the container's very own layer, and it's where all the action happens. This whole thing is made possible by a really powerful file system mechanism called copy on write, and this is the key that connects the static read-only image to the dynamic running container. So if your container needs to modify a file that exists in one of the read-only layers below, Docker doesn't touch the original. Instead, it copies that file up into the writable layer before it applies the change. Let's just walk through that real quick. Say your app tries to modify a config.json file that's living deep down in a read-only layer. Docker's storage driver sees this and intercepts the write operation. First, it copies the original file up into the top writable container layer, and only then is your change saved to that new copy. The original image remains completely pristine, totally untouched. And as you can imagine, this architecture is incredibly efficient. You can have hundreds of containers all running from the same base image on a single machine. They all share the read-only layers in memory, which is super efficient, but each one gets its own private, isolated, writable layer. This guarantees that no container can ever mess with a base image or interfere with any other container. So we've covered storage efficiency and runtime isolation, which are foundational. But this layered model has another massive benefit, one you'll feel every single day: build speed. This is where the architecture truly shines and can save your team countless hours. So let's talk about build caching. The golden rule here is really simple. If the Dockerfile instruction that created a layer hasn't changed, and none of the layers before it have changed, Docker is just going to reuse the cached layer from a previous build instead of rerunning the command. It's that simple. And this has huge implications for how you structure your Docker files. On the left here, we're copying all of our application code in first. This means any tiny code change invalidates the cache for that layer and every single layer after it, forcing a slow reinstall of all your dependencies every single time. The optimized version on the right, though, it copies just the dependency file first. Now, that stable dependency layer is only rebuilt when that one specific file changes, which is way less frequent, making our builds dramatically faster. Okay, so we've built our lean, efficient, perfectly cached image. How do we share it with the team or get it to production? Well, that's the job of an image registry, like the public Docker Hub or a private one you might host yourself. Just think of them as the central libraries for storing and distributing all these image blueprints. And guess what? The layered architecture makes this process incredibly network efficient too. When you do a Docker push, only the specific layers that the registry doesn't already have are actually uploaded. And same thing on the other end. When a server runs a Docker pull, it only downloads the layers that it's missing. You're not sending the entire 800 megabyte image every time, just the little tiny bits that have changed. So why does any of this matter? Why obsess over these internal details? Well, because this layered architecture is what directly leads to faster CI/CD pipelines, perfectly consistent environments from your laptop all the way to production, and the ability to efficiently scale our applications. It is the absolute foundation of modern containerized infrastructure. And when you really master this mental model, the results can be pretty dramatic. Advanced techniques like multi-stage builds, which are built entirely on top of this layered logic, can reduce your final production image sizes by up to 90%. That creates lean, secure, and incredibly fast-deploying applications. So let's just summarize the core mental model you should walk away with. A Docker image is a stacked, layered, read-only blueprint. A container is just a live, running instance of that blueprint with one unique, writable layer placed right on top for all its changes. If you get that, you get the heart of Docker. This whole elegant, layered architecture isn't just some clever technical detail, it's the fundamental innovation that makes Docker practical, scalable, and efficient enough to run a huge chunk of the world's modern infrastructure today. So I'll leave you with a question to take back to your own projects. Now that you really understand how these layers and the caching actually work, how are you going to structure your next Docker file to make it as efficient and as fast as it possibly can be? Thanks so much for joining us on DevOps Corner. If you enjoyed this deep dive and it helped things click for you, be sure to hit that like button and subscribe for more explainers that break down how modern infrastructure really works.